Hello and welcome back in our class of Eurocode 7, application of retaining wall. This is application of Eurocode in France and design of retaining wall, like you see on this photo. So with this video, we will try to start a new chapter, chapter number 2, which is about some assumption and input data. So this is just to let people know the assumption made in the before going in the calculation. So we will not go really deep in detail. When we start calculation, for example, in this chapter 5, the example, we will go deeper in the detail. Here we just introduce some concepts briefly. Okay. So assumption and input data. This video will cover this point, the earth pressure, which is very important in the case of retaining wall, design of retaining wall. Okay. So not land, okay, earth pressure, sorry. The earth pressure at rest when the soil is not moving, okay? So what we want here is the lateral earth pressure, because the lateral earth pressure is the one that is acting on your retaining wall, okay? So you need to know the value of that lateral pressure. And this lateral earth pressure is obtained by using this K naught. This K0 is the coefficient of the earth pressure at rest when the soil is not moving. So this is the ratio between the horizontal effective stress, sigma prime H, and the vertical effective stress, sigma prime V. I think you know that already. So K0 is this sigma prime H divided by sigma prime V. Effective horizontal pressure, horizontal effective stress, and vertical effective stress. So this coefficient is influenced by the nature of the soil and its history. Means, for example, if the soil was loaded before, or if the soil have never been loaded before. And it depends also, in particular, the history, in particular, the state of compactness, if the soil is compact or not. In the case of uniform soil, homogeneous soil, semi-infinite massive of soil, and horizontal surface, and no lateral deformation, in that case, we can use this formula to estimate the K0. Okay, this one is Poisson ratio of soil. This formula of K0 is not really effective. Sometimes it can give you some value of K0 that are not realistic. Okay, so in practice, how do you estimate K0? How do you estimate the value of K0? You can get it from the expression relating in the drain friction angle, the friction angle, and the effective preconsolidation pressure. You can get this with this relationship. And also, using some lab test, the drain trajectory test is with zero radial deformation. This can give you also K0. Edometric test. Maybe I think you know this one also. That can also give you the value of K0. And in situ tests, in test in place means in situ tests, like self-drying pressometer, which this test can give you. See this pressure ball inside, you insert this in the soil, and this gas, the bottle of gas, will the pressure, the displacement and pressure can be obtained here in this acquisition system. Another one, this is a Marchetti dilatometer. I think this one is a Italian invention and is according to European norms. You insert this in the ground just by heating it, and actually there is plastic membrane around this. This is like a blade, you know, and you insert the blade in the ground. After inserting, for every, I think every 20 centimeter or 25, I'm not sure, you measure the pressure, the necessary pressure to displace 1 millimeter or 1.1 millimeter. Okay, so it means the air here, the gas here, is used to the plastic, because the membrane is in the plastic. The membrane is made of plastic. So by sending the gas will put pressure on the membrane, and it will be enlarged like this. And the pressure obtained here is P0, means no pressure. And if you want to measure the displacement, the pressure corresponding to the displacement means by sending the gas in the membrane, the displacement the pressure corresponding to displacement of 1.1 millimeter is recorded. Okay, this is how we obtain K0. There are different ways of obtaining this K0. Maybe you can get more information, but this is just some examples. Okay, so the most common formula for this analytical formula, theoretical approach, is in case of normally consolidated soil and horizontal surface, means the surface is not inclined, okay, horizontal, then you can use this formula as formula of K0. 1 minus sinus the phi prime, okay, the friction angle. And for over consolidated soil, this one is normally consolidated. For over consolidated soil, then you have to use this, the over consolidation ratio. Okay, this one is simple one, normally consolidated, this one. But if the soil is over consolidated, then you have to use the over consolidation ratio, which I think you know, sigma prime P, means pre-consolidation constant, pressure of pre-consolidation, divided by effective vertical stress, effective vertical stress. Okay, at rest. You can find this in this more information in this reference. Okay, in the case of incline slope with the angle of inclination beta, means the soil, the retaining wall is like here, and the soil is not horizontal. Okay, the soil behind the wall is like inclined. In that case, you have to add more. You have to add this part. 1 plus sinus b beta. You have to add this angle. This is same angle here, inclination angle. And this K0 is this one or this one. In case of normally consolidated, you use this one. Normally consolidated with slope, you use this K0 and you multiply by this time. In case of over consolidated soil, the K0 will be this one. So the K0 here in that case will be this one. And if there is slope, then you add this part by multiplication. Let's talk now about the F pressure at rest. I think it finished. So let's talk now about the active pressure and passive pressure. Movement necessary to mobilize the limit balance. The thing is, when you install a retaining wall, if there is no movement of the soil, of the ground, the wall will not be working at all. The soil has to move so that the wall will work. If there is no passive pressure and no active pressure, means it's just the same as the pressure is, there is no pressure acting on the retaining wall, then the retaining wall is not working at all. So we need at least minimum movement of the soil to allow the equilibrium. That's why we are talking here movement necessary for the mobilization of the limit balance. The limit balance is, so calculation of active and passive pressure must take into account the amplitude and direction of the relative movement. How much the wall did move and in which direction the wall did move. Okay. So limit equilibrium or passive or active pressure is only reached if the wall deforms. In case your wall is flexible wall, then the limit is reached only if the wall deforms. Or in case your wall is not deformable, the wall is rigid wall. In that case, the limit is reached when the wall undergo sufficient movement. The wall has to move. The minimum movement is needed. So if we take a wall, for example, like this, let's consider that this is a wall. If this soil behind the wall is not moving, and here also there is no movement, generally the movement starts from here. If there is no movement, so this means the wall here is not working. Okay, let's take example of clay. If you are digging, you want to dig a hole diameter of 1 meter, for example, in the clay. If the clay, the cohesion is high, you can dig without even retaining wall vertically, and it will not fall. In that case, you don't need retaining wall. It means the cohesion behind the soil behind here is enough to maintain the soil mass. That's the meaning. In that case, any retaining wall here is not working. So for the wall to work, it has to move. So let's take that in an example of a retaining wall. The height of the retaining wall is h. Okay, retaining wall is h. So the minimum movement we need in case of active pressure, this active is here, this side. Okay. For the active pressure to be mobilized, small displacement in the order of h divided by 1000 to the 5 times h divided by 1000 is needed. So it depends on the height of your retaining wall. Okay, the total length of, for example, the pile or anything you use as the structure of your retaining wall. In case of passive pressure, the minimum movement necessary to mobilize this passive pressure is h divided by 100 to h divided by 10. So that one is larger. We need a larger movement to mobilize this. For example, if your retaining wall, the height is 10 meters. So for example, you can take 10 divided by 10, it means 1. So 1 meter, displacement of 1 meter before this one be mobilized, for example. Or 10 times means 0.5, 0.1 meter before it be mobilized. Between 0.1 to 1 meter. Okay. This is just a range before it be mobilized, this passive pressure. So at a given point of the wall, it is the local movement that must be considered and not the overall movement of the wall. Local movement, for example, around here, if around here the movement is enough, so around here the pressure will be mobilized. And if only around here the movement is enough, so around here the pressure will be mobilized. So this is the meaning. So we are not considering the whole movement, but localized movement. And now for closed wall means you have, for example, 2 rows of walls. Higher passive pressure value can be considered where appropriate, taking into account the limited interval between the 2 walls. So in case of you have 2 closed walls, one retaining wall here and another wall here, if they are close, considering the interval between the two, higher passive pressure value can be considered. Yeah, anyway, this was about the movement we need to mobilize. You need that all these are just assumptions, okay? Now let's talk about the value of the pressure themselves. What should be the limit of the earth pressure? Determination of the earth pressure limit value according to the standard, this French standard. Calculation of the limit active pressure and passive pressure is carried out by applying the principle of superposition of equilibrium state and to take into account the cohesion by applying the theorem of corresponding state. This is just to say that the theorem of superposition is you add the effect of cohesion, adding effect of unit weight, adding effect of the charge, this kind of thing. I think the bearing capacity formula of Terzaghi also is obtained by theorem of superposition. Okay, so this French standard, which is application of Eurocode 7 in France, proposed to determine the value of the active pressure and the passive pressure of the earth under the effect of volume. Actually, this is unit weight, uniform overload. This is the charge. For example, we can have here charge. If here is charged by charging, loading here, loading the overload, and the cohesion, if the soil is cohesive, okay, from the coefficient of proposed by this carousel and Absi. This book is giving the coefficient of F pressure. Okay, this is table of active and passive earth pressure. Okay, if I take this example, for example, if you have this active and this passive, when the earth is at rest, the soil is not moving, then you use K0. Okay, the K0 we have talked about the beginning of this video. K0, when the soil is not moving. But in case of this here, soil, the soil mass behind the retaining wall is moving. The force acting on the wall is called passive. This is passive pressure. Sorry, this is active pressure. A for active. Active pressure because the soil is acting on the wall. Okay. Active pressure because the soil is acting on the wall. The passive pressure because this one is actually retaining the wall. Okay, so in case of this condition, you cannot use the K0. You have to use Ka, means active in case of active, or Kp in case of passive. See, active, passive. So this book is giving you the value of this Ka and Kp. In K0, in case of the earth is at rest, the earth is not moving, you use K0. But when you are in this situation, it is moving, the soil is moving, the earth is moving. Okay, and acting on this wall. So active pressure. In that case, you cannot use K0 anymore. You have to use Ka in case of active pressure, Kp in case of passive pressure. And this value of Ka and Kp are given in this book. And then here it's saying that we can obtain these values are obtained by using the theorem of superposition. Okay, it means you use the effect of unit weight plus the effect of the charge overloading plus the effect of cohesion. Okay, exactly like the formula of Terzaghi for bearing capacity of shallow foundation. I will just keep this here. So the active pressure and passive, the active, actually this one is should be passive, active and passive pressure. Okay, sorry, have correct here. This coefficient of heavy and this rubbing ground means the friction ground. Okay, heavy, it means the soil has unit weight. Okay, so you have Ka gamma, Q, Kp gamma. Okay, so all these value are in this book. So for this time, we will not go deeper about this value, but next time we will talk deeper about them. But you can find them this reference. Okay. So the coefficient are given in the active pressure and F. Active pressure, this table on active and passive F pressure as a function of the friction angle. So you will find the different value depending on the friction angle. Depending of this angle is lambda is the inclination of this, the inclination of the retaining wall. Okay, this retaining wall, if it is inclined with this angle, and also the beta is this angle, the slope, inclination of slope, in case of the ground is not horizontal. And this angle is this one, the inclination of the resultant, the equivalent of the active pressure and passive pressure. So it means the value of the coefficient given in this book, these value are all function of these parameters, phi prime, this lambda, beta, and this way small delta. Okay, yeah, all the situation are almost all situations are covered in this book. You can just get, and by applying Ka, you multiply by the gamma, the unit weight, multiply by the depth, and you get your horizontal half pressure, active one and passive one. That one. So the diagram of the pressure for heavy, then rubbing coherent. Coherent means cohesive actually, but it's tradition from French. And loaded soil, it means you have unit weight, you have cohesion, you have the charge. Okay, in that case, you will obtain the total pressure by using the superposition. You are the effect of the weight, not heavy actually. The weight and the friction angle. You are the effect of the cohesion, and you are the effect of the load, the charge. Okay, in case you have load here. Then the coefficient proposed by this book, these coefficients are based on the Boussinesq theory with the assumption are like follow. Maybe you know already the assumption of the Boussinesq, the inclination of the pressure, this angle, small delta, determined at the priori by designer. So you define your inclination. It's up to you. The sleeping line, the failure lines, these lines, I think here is around here should be the ranking theory and Boussinesq, ranking Boussinesq. We will come back on this later. These lines should be plain line and logarithmic spirals. the ranking equilibrium, the stress distribution depend in the ranking equilibrium, the stress distribution depend on the depth and the inclination angle, this angle. This is just assumption. All this part of this chapter is just about assumption. All this chapter actually, not only this part, and input value. So let's take now in case of frictional ground. The ground is just cohesive ground. The cohesion is strong. The ground has large cohesion. And I think as I was explaining, when the cohesion is large, sometimes you can dig even deep without the need of retaining wall. You don't need any retaining structure if the soil has good cohesion. You can dig, for example, a hole on diameter of 1 meter, for example, or 2 meter, and until a certain depth, for example, 1 meter in clay, for example, and try to do this in sand. It will not stand. It will collapse inside the hole. Okay. Try to do it in dry sand. It will not hold. So that's why in case of the cohesive soil, taking the cohesion into account result from the application of the theorem of corresponding state, which can be stated as follows. You can use this reference to check what I'm talking about. The limit equilibrium condition of the cohesive mass, not coherent actually, cohesive mass can be calculated as if the mass were cohesionless, not powdery, just like powder, means like sand. This is directly translated from French. Just consider cohesionless soil with same angle of friction, internal friction, same geometry, and the cohesion mass subjective to the same external forces, to which is added the compressive stress uniform intensity C multiplied by cotangent of phi prime over the entire outer counter of the massive. The meaning of this means, it means that if you have cohesive soil, you can consider that this is not cohesive soil, cohesionless soil plus the effect of the cohesion, which is just here. A load you add, this is the equivalence of the effect of the cohesion. Cohesion multiplied by cotangent of phi prime. That is the meaning. Okay. Then, as I was saying, if the cohesion is strong, the cohesion is high, it means sometime that cohesion will be helping the wall, will be stabilizing the soil mass behind the wall. So it will decrease somehow the active pressure. The pressure that is acting on the wall will decrease. It will be like minus. On the other hand, it will increase the resistance here. It means the passive pressure will increase because the cohesion. So that's why the reduction in the active pressure, reduction on active pressure, it will reduce the active pressure on the wall because the cohesion will retain the soil mass, so that the active pressure behind the wall will not be that much. So that reduction can be expressed as this formula, with this formula. And the decrease of passive pressure can be given by this formula. This K, in this case, the KQ is the active pressure coefficient. But in this case, it is the coefficient of passive pressure, not active again, sorry. I don't have to correct this, so just consider that this is passive. Okay? This is how we get the contribution of the cohesion. So this contribution is normal to the wall. So it's going in this direction. Okay? And it constant with depth. If you take, for example, the earth pressure is like this triangle, or even the water pressure is like this. But this contribution of the cohesion is just like this, uniform with when you go deep with the depth. It's uniform. Okay? And sometimes what happens is, in case it is very simple, the simple case means the case where the wall, vertical wall supporting horizontal platform, horizontal soil, horizontal ground, the cohesion, the term for cohesion becomes like this. Okay? This epsilon multiplied by C square root of K, where this epsilon is the number that is varying between 2 and 2.57. Okay? So, in case of you have smooth contact, this will be 2. The epsilon will be 2. The rough contact, the epsilon will be 2.55. Okay? So, in the absence of specific recommended analysis of this parameter, it can be determined consistently with this assumption made on the inclination of the active pressure. In that case, you can obtain the formula, the epsilon, using this formula. Okay. So sometimes it happened that because by subtracting the effect of the cohesion, the active pressure becomes negative. But since we cannot have, the ground cannot pull the retaining wall, so in that case, you need to correct the pressure. The ground will never be able to develop traction on the wall. So in case of you remember I said the contribution of the cohesion should be subtracted, because the cohesion will be helping to maintain the soil mass behind the wall. So by doing sometime minus the effect of the cohesion, you can get somehow negative pressure, like here, for example, negative. So in that case, you have to correct them. You can see here, these are corrected. Sorry, it's in French, but this is when we correct, it becomes something like this. We'll come back on this in the examples, as I hope. Okay, so it will be more clear. So in case of some soil that are not rocks, it is sometimes safer to take into account effective pressure on the wall at a given level. At least you should take the pressure which is at least equal to the 1/10 of the effective vertical stress at the same level. 1/10, 1 divided by 10, 1/10. So if following from this arrangement, this is just for safety. In that case, the total stress applied to the wall below the level of water table is at least equal to the hydraulic active pressure increased by this amount. Okay. What this is trying to tell you is just it is safe for you to take at least pressure, effective pressure acting on the wall, which is at least 1/10 of the effective vertical stress. Yeah. If you calculate, for example, the diagrams here, and it giving you something less than 1/10 of the vertical stress, don't take that. Take at least the minimum 1/10 of the vertical effective stress. That is the minimum. Okay, just for safety. This is recommendation. There is another method, we call this the active pressure, using determination of active pressure using the Coleman, or I don't know how to read this, Coleman method. Maybe Coleman method. So this method is just graphically, in case you cannot obtain the pressure, the active pressure, using analytical formulas, using theoretical formulas. So when the geometry is complex condition, we will talk in detail about this method also later. So when it is complex, geometry is complex and doesn't allow the active pressure forces to be determined analytically, then we can use this Kalman method. Okay, this method generalize is just generalization of a Coulomb theory based on rectilinear failure lines. The failure lines, not breaking line. This implementation of the Coulomb's graphic, the Coulomb, graphic construction, make it possible to calculate the resulting force acting on the facing of the wall for when you have non-homogeneous, non-uniform ground. Okay, and the embankment of any shape, if it is really complicated shape, the topography behind the wall is very complicated. It's not horizontal, and the slope also is sometimes even it has some excavations. So in that case, this method is giving another alternative to calculate the active pressure. So the graphic of this method allow the overall determination of active pressure acting on a plane retaining wall by a retained mass of any geometry. It doesn't matter the geometry, this method can work. So it makes then possible to define the active pressure that is exerted on the wall by integration of a positive or negative load, depending on whether the surface of the slope is above or below the average slope line. Above, or it means you will have sometime this kind of topography going like this. Not the line, it is not a line like this or horizontal like this. Topography is just complicated shape. In that case, this method can give you the active pressure. So this method, it does not explicitly involve the concept of active pressure coefficient, the Ka. It doesn't involve that explicitly. Okay, so for this video, we'll just stop here and continue next time with the second part of this chapter, which is, I think, this obliquity. Okay, thank you very much and see you next time.